Welcome, I'm Raymond Hoofs. I work for the European Space Agency with science operations planning of our planetary missions, and I'm going to give an overview of the planetary science missions that we have in orbit, that have been completed and are in post operations, and the ones that we are planning. Then we can go to Mercury, where we have the BepiColombo mission. BepiColombo mission is a cornerstone mission, which means it's a big ESA mission, and on top of that it's a collaboration between ESA and JAXA. So it combines two spacecraft. It combines the Mercury Planetary Orbiter, the MPO, which is done by ESA, and the Mercury Magnetospheric Orbiter, the MMO, which is done by JAXA. And then there is actually a third component of this, which is the MTM, the Mercury Transfer Module, which is a module that contains electric propulsion to move these two spacecraft on its interplanetary voyage to Mercury. It's quite a complex trajectory to get to Mercury, so if we launch it at 2018, it will arrive there late 2024. Both spacecraft which will work together but have different focuses. The MPO will give high resolution imaging from an orbit that is about 2.3 hour period, 480 kilometers close to Mercury at its pericenter, and the MMO will have a much larger orbit going out further to characterize the magnetic field around Mercury. So they will be working together. MPO will also have magnetic sensors on board, and this data will be shared to get the full picture of the Mercury magnetic field. BepiColombo is a very complex mission. It's an extremely complex spacecraft. This is mainly because the temperatures at Mercury are so high and a lot of new materials needed to be developed in order to make this possible. I'm going to show you a video that shows the material development of some key components of the MMO, and it will show what are the challenges that we are facing with developing these materials.
My name is Přemysl Janík, and I'm a material and process engineer at the European Space Agency.
My name is Laurence Levent. I'm a space material and environmental testing engineer at the European Space Agency.
BepiColombo will be the first Europe's mission to Mercury. It is a joint mission between ESA and JAXA, Japanese Aerospace Exploration Agency. When the spacecraft arrives at Mercury's orbit in 2025, it will face extremely harsh conditions. The temperatures as low as -190 degrees Celsius in excess of 450 degrees C. It will also be exposed to strong ultraviolet radiation and electron and proton fluxes for the entire mission duration. Over that time, we need to rely on the performance of all materials and components used on a spacecraft.
The ESA Material and Electrical Component Laboratory was approached by the mission team BepiColombo to test and improve the stability of the coating foreseen for the high-gain antenna. The antenna had to be manufactured to extremely high accuracy. Any overheating or reduction of its performance will result to a high risk for the mission and results for a loss of data in case we cannot communicate with the spacecraft. The ESTEC Star2 facility is a facility where we can expose simultaneously samples to UV intensity and radiation particles, simulating the harmful part of the sun and measuring at the same time the performance of the material as if we were in space. For the antenna, it was important for us to test its ability to reflect the incoming radiation and emit the heat. As we refer to the solar absorptance and high thermal emittance, these two properties help us to regulate the temperature of the antenna, which we aim to keep below 450 degrees Celsius.
After the initial test, we identified two prospective ceramic white coatings which showed quite good resistance to high temperatures and UV radiation. These coatings were later tuned with a specifically doped coating so we could reduce the radio interference.
Of the two samples, we use a range of methods to achieve samples with different thicknesses and different adhesion strengths. For us, the challenge was the risk of cracking of the coating, and for that we had to analyze the surface with sophisticated electron microscope. Then after, the samples were mounted on a sample plate and exposed to UV radiation.
Visual inspection after UV radiation exposure showed we faced a major challenge. We noted very strong discoloration effects on the first set of exposed samples. We had to carefully analyze these samples to understand what was the root cause of the darkening.
We also checked the adhesion of the coating to assess whether the surface layer will peel away after high intensity UV exposure by applying a tape test. And after improvement, our final coating shows sufficient adhesion strength.
With our industrial partners, we introduced several improvements to the coating process, so we could significantly increase its performance over thousands of simulated testing hours. In the end, we developed the coating, which will not only survive the conditions around Mercury, but it will maintain its performance over targeted range of our mission. We are really looking forward to the launch of BepiColombo in the near future, so we can demonstrate how our team has contributed to the first Europe's mission to Mercury.
After the completion of Rosetta, I will also be working on BepiColombo again. I've been working on BepiColombo before Rosetta arrived at the Comet, and I was much involved in preparing for the science planning around Mercury. But in order to do good science planning, it's very important to understand really well the experiments that are on board of the satellite. And in order to gain that experiment, I'm also involved in the test environment, where we're actually mounting the experiments on the spacecraft and we're testing out how they work. So when you're doing these tests, you're checking out that all these experiments are working in the correct way to operate at Mercury. At the same time, you learn exactly how these experiments work, how they operate, which kind of operational modes do they have, how much power they consume, how the data of the experiments goes through the spacecraft and then comes out for the experiment teams to observe what their instrument actually has done. So the test environment is an extremely interesting environment to be involved in, and we're gonna also look at a video showing this test environment, and it shows how these spacecraft need to go through a number of tests on ground to make sure that they're ready for operations in space. This video will show the BepiColombo MPO spacecraft in this test environment, and often people think about spacecraft only being in space, but of course we do need to build these spacecraft on ground, and when you test them, then of course they are actually one of the most dangerous environments, which is the environment on Earth, where there is gravity and people can make mistakes and you can actually damage the satellites as well. So we need to do all of this work with extreme care. We see in this video, we see the MPO spacecraft as it is being prepared to go in the solar simulator at ESA. It's a simulator that was upgraded for the BepiColombo mission. It simulates spacecraft in space. But for BepiColombo we had to increase the solar intensity, so the lamps were increased in power such that they could provide the power of 10 times the solar constant to simulate the Mercury environment. We see here the spacecraft being put into this solar simulator. The spacecraft has a very clear side with radiators, which is these lined structures, and then you see 4 red spots, which are the covers of the star trackers. Those have to be turned away from the sun, so you will see that they mount it in the solar simulator in this way, so that that panel is turned away or cannot have any sun shining on it, and for the rest it's covered with white thermal blankets to make sure that the temperatures outside but also inside do not get too warm, because of course inside there's a lot of electronics that cannot overheat. We see in the solar simulator that the spacecraft can be put under different angles, so we can see and observe with thermal sensors in the spacecraft how the spacecraft thermal insulation behaves to the different positions of the Sun. The next mission to observe the Sun will be Solar Orbiter, which is to be launched in 2018. And it will explore the Sun in an unprecedented detail. It's an ESA mission, but has important contributions by NASA as well. And after launch, it will take about 3 years before it gets its operational orbit. And then it should remain there for 7 years at least for the nominal mission around the Sun. Now the minimum distance of Solar Orbiter is closer than the orbit of Mercury. So it will have a period of about 168 days. And the minimum perihelion radius will be 0.28 AU, which is the distance closer than Mercury. It will change the inclination of its orbit as well, such that as the orbit progresses, it uses Venus gravity assist in order to tilt its inclination, such that also it will have a view of the poles of the Sun, which will be really new information to give further insight in study of our Sun. Then there will be the Jupiter Icy Moons Explorer, the JUICE mission. This is to be launched in 2022 and should remain operational until 2033. And it's a mission to Jupiter and mainly its icy moons. It has a very large interplanetary voyage to Jupiter of 7 years. And when it arrives at Jupiter, it will operate there for at least 3.5 years. First around Jupiter, making flyby of moons, and then it will actually go into orbit around one of the moons, which is then the moon Ganymede. So it's an extremely challenging mission. It will be done using solar power. So Jupiter is very far away from the Sun, so it will have very large solar panels. It is currently in development, and it is planned to be launched in 2022 on an Ariane 5 rocket. So the last mission to mention in the view of the planetary missions is the Asteroid Impact Mission, AIM. It is planned to be launched in 2020, and it is part of a bigger mission called the Asteroid Impact and Deflection Assessment Mission, AIDA, that is done together with NASA. So this mission is to check how an asteroid can be deflected in the future if an asteroid would come to Earth. And the idea is that the Europeans will send the AIM mission to the asteroid, a small asteroid. It's actually an asteroid with a moon. It's a binary system. And the Americans will make the double asteroid redirection test, or the DART mission. And that's a satellite that will impact with this moon, and we will analyze the deflection of this moon after it's been impacted. So the AIM mission would go there first, map the orbit of the moon and the surface of this small asteroid, and later there will be the NASA mission to do the impact on the moon, and then we will analyze the deflection. It's a very interesting mission, of course, in view of future asteroid deflection on Earth to protect the Earth, and it's at the moment under study. Then I will now show a video that shows many of the aspects of this AIDA mission, showing the arrival of AIM and what it will do in preparation of the NASA DART satellite arrival.
If an asteroid was ever headed our way, what could be done about it? ESA and NASA plan to test if a technique called kinetic impact would work to deflect it. The Asteroid Impact and Deflection Assessment Mission is made up of 2 spacecraft, the US-led Double Asteroid Redirection Test and the European-led Asteroid Impact Mission. Headed to the Double Asteroid Didymos system, ESA's AIM has 3 objectives: to see if asteroid deflection is feasible, to test deep space laser communication systems, and to perform scientific investigations on the asteroid system. AIM will be launched in October 2020 in order to rendezvous with Didymos in May 2022. AIM will be humanity's first probe to reach a binary system. The larger asteroid is orbited by a smaller one, known as Didymoon. Upon arriving, the spacecraft will take its first high-resolution pictures of the binary system. AIM will scan the smaller Didymoon closely with its visual imaging system, gathering information on its orbital dynamics as well as its physical characteristics. High-resolution surface mapping will chart the surface landscape and provide invaluable data for the targeting system of DART. The results will be beamed back to Earth by a high-bandwidth laser communication link. Engineers will try to push the limits of this instrument to work also as a laser altimeter and an infrared camera while operating in close proximity of Didymos. AIM's high-frequency radar will probe the first layers beneath Didymoon's surface. This will help engineers to fully understand the structure and model DART's impact. Thermal imaging will reveal more surface properties, including the soil structure and cohesion. Next comes putting down a lander developed by the German Aerospace Center, which will return data back to AIM. In particular, the lander will emit low-frequency radar waves that will pierce right through the asteroid to the other side, allowing AIM to chart Didymoon's deep interior structure. Several tiny CubeSats will also be released from AIM to perform further scientific monitoring, while also testing inter-satellite links in deep space. Once this pocket-sized rock is explored, AIM will move away to a safe distance, as the US DART mission is on its way. DART will target Didymoon and then crash into it, deep center. The impact will be monitored both by AIM and its CubeSats. Thermal images of the moment of impact should give an idea of how much and what type of debris is ejected from Didymoon and how far the resulting plume will reach. The next question is, how will the impact alter the orbit of Didymoon around the larger asteroid? In the aftermath, AIM will move closer to Didymoon to find out in conjunction with ground observatories. AIM's high-resolution view will assess the size and depth of the crater left by the impact. The lander will repeat its low-frequency radar transmissions through the asteroid to reveal any major changes to the asteroid's internal structure. Meanwhile, AIM will also perform a second set of detailed radar and thermal probing for detailed comparison of the situation before and after impact. AIM is being developed by the European Space Agency, while DART is concurrently being developed by NASA, jointly with the Johns Hopkins University Applied Physics Laboratory. Together with the German Aerospace Center and the Observatoire de la Côte d'Azur, they form the AIDA team, which supports the Asteroid Impact and Deflection Assessment mission.
Finally, I want to give you very quickly an overview of the astronomy missions. As I said before, I'm myself not working with the astronomy missions, although they are all operated from the center where I work in Madrid, called ESA, the European Science and Astronomy Center. So just an overview of these astronomy missions. These missions are in general telescopes in the sky. They are in general directly around Earth in order to get the data very quickly down, and they can produce a lot of data. So they cover the whole range of the electromagnetic spectrum. So we can start with the Planck mission. That's one of the missions that looks in the view of microwaves. Then we see Herschel to the sub-millimeter infrared, and then actually we see JWST, which is the follow-up, if you want, of the Hubble Space Telescope, but it's a much bigger telescope looking more to the infrared direction. So this is a very huge project that is going to be launched in the next couple of years. That would really give extremely interesting data. There is the Euclid mission that is going to be focusing on this information of the dark universe. And then there is Gaia, that is at the moment observing all the billions of stars that are out, is mapping out the stars. Then of course there is the Hubble Space Telescope, that also ESA has a very big contribution to continuing to observe many things in the astronomy, but also in the planetary system. And we have the XMM Newton telescope doing the observations in the X-ray to be finally completed, the spectrum with integral doing the observations in gamma ray. Then there is one more, which is a LISA Pathfinder mission that was launched about a year ago in order to detect gravitational waves. This is a mission that falls under the fundamental physics and is there in an area that is really still very new and is being developed.